It is now 2016. Human emissions have caused CO2 levels to triple compared to the pre-industrial era, leading to a worldwide temperature rise from minus 0.25 degrees to 0.75 degrees in just 100 years, and a 4-degree rise by 2100 has been predicted by some models. It is critical that we change our behaviour now, reducing our dependence on fossil fuels and turning instead to more sustainable power sources. We are 6 aeronautical engineering students from Imperial College London, and we were set the task to design and make a small-scale wind turbine. Wind, as well as hydro and solar power, is one of the ways that we can produce sustainable power. Already, wind power makes up 9.5% of the UK's total power production, and this figure is set to rise. By developing this technology for small-scale units, we hope that insights can be made for the integration of wind power for regular households. The horizontal axis clockwise rotating turbine was to have a diameter no larger than 400mm, with a total mass under 400 grams. Furthermore, the turbine was to be designed to self-start at wind speeds of 10 meters per second, with a maximum angular velocity of 3000 rpm, and produce max power at tip-speed ratios of between 3 and 8. Our main aim was to minimise the mass of the turbine, the amount of power produced.
The turbine is designed to have maximum allowed diameter of 400mm in order to maximize the power available for extraction from the wind. In this equation, Cv is the ratio of the power extracted by the wind turbine over the wind power. Airfoils were compared using the University of Illinois database. Overall, the FX6100 and SG6043 were shortlisted as they were designed for wind turbines and optimized for low Reynolds number, which is applicable to our design requirements. We finally chose the SG6043 airfoil for its high optimum lift coefficient, at which lift-to-drag ratio is maximized. This allowed a narrower blade profile for a two-bladed design according to the Schmidt's distribution. It resulted in the blades to be more aerodynamically efficient and have a lower mass. However, it also reduced the blade capability to self-start. The highest LD ratio was achieved at an angle of attack of 6.5 degrees, which has a lift coefficient of 1.25.
The tip speed ratio is the ratio between the rotational speed of the tip of the blade and the incoming wind speed. In order to satisfy the requirement of 3000 rpm at maximum performance, the chosen TSR could not exceed 5.2. We decided to go with a TSR of 4.5 to make sure we didn't exceed the design constraints during testing. As we move from the axis further along the blade, the rotational speed increases, while the incoming wind speed remains constant. Hence, the relative wind speed varies in both magnitude and direction. To ensure the aerofoil was at a constant angle of attack at its optimum, its orientation had to change with the distance on the axis. Its size had to vary as well so that the power extracted was maximum. In addition, we took into account the wake losses due to the wake rotation downstream to arrive at our definitive pitch and chord distributions. These are the Schmidt's equations. We made a 15-degree cut at the wingtip and rounded off the edges to reduce the turbulence generated due to sharp corners and blunt tips.
The cone was designed with the smallest possible diameter of 36mm in order to maximize the length of blades. The small hop and the minimized length of 12mm reduced the overall weight of the turbine, while still guaranteeing the structural integrity during the test. The nose was shaped according to the Hack formula to reduce drag, and its length was minimized as the mass saving outweighed the aerodynamic benefits. It was made hollow to further minimize the mass. We used a modified SG6040 airfoil section to connect the blades to the hub. The trailing edge of the airfoil was modified as a blunt edge. This brings us 3 advantages. Firstly, this avoids the high stress intensity in thin trailing edge. The flow separation occurs further downstream than the regular elliptical cross-section, and this reduces the drag. By choosing an airfoil of the same family as SG6043, the transition from the root section to the blade is smoother. The octagonal hub was designed in order to relieve the stress intensity while maintaining the grip between the hub and the cone. We also drilled holes to reduce the mass to just over 9 grams.
After designing the aerodynamics of the blade, we had to check the turbine would not fail during testing. Using MATLAB, the distribution of aerodynamic and centrifugal loads was simulated along the blade, at the maximum testing speed of 12 meters per second, and over a range of RPM. The following assumptions were made to simplify the calculations. First, the beam was discretized into 20 parts. The second moment of area was assumed constant between each section, and lastly, twisting was neglected during testing. Using simple beam theory, we integrated twice the aerodynamic loads distribution to get the bending moment distribution along the blade. We estimated the maximum stresses in the horizontal and vertical direction occurring on the blade surface due to those moments. We then calculated the centrifugal stress distribution along the blade, which was found to be vastly superior to the stresses due to the aerodynamic loads. It was found that the turbine could handle up to 9,500 RPM before reaching its failure stress of 21.6 MPa at its root. This would be largely above the maximum RPM the turbine would experience, even against a 12 meters per second wind speed with no hysteresis brake applied. However, the assumptions made to simplify the analysis could have altered the results. In order to verify the validity of our model, we conducted finite element analysis using Creo. It revealed the highest stress concentration at the root tip. However, the stress was still way below the failure stress of ABS plastic. The deflection of the turbine in the rotation and axis direction due to the aerodynamic load was also estimated. The high deflection could have altered the aerodynamic behavior of the turbine and caused stall. Overall, the deflection in the rotation direction was found to be negligible, and have only 2 cm at the blade tip in the axis direction, which would not be sufficient to cause stall.
Overall, the 3 key features of our designs were low mass of 54 grams thanks to the short hub and a small hollow nose cone, a customized root section to improve the turbine's aerodynamic properties. Finally, a hex series nose cone was used to minimize the drag.
The blades and hub were produced through 3D printing of ABS plastic. The turbine diameter of 400mm, as stated in the project brief, was smaller than the maximum printable size of the 3D printer, which allowed us to design the blades and hub as a single part. This meant no joining was required, and as a result led to a stronger turbine. The 3-dimensional model required for the printing was produced in Creo parametric. The aerofoil shape was imported as a spline using a series of data points, and the nose profile was similarly created from a spline, with data points produced using the hack series equations in MATLAB. The key was manufactured from a circular stock of aluminium. Using a CNC lathe, the shaft hole was formed and it was reduced down to the desired diameter. Following that, the workpiece was transferred to another CNC machine, the VTC 200C, and given its octagonal shape. 2 holes were then drilled into 6 of the sides in an effort to reduce mass, with one final threaded hole being introduced with the grub screw. Finally, the keyway was formed through broaching. The blades were finally sanded to a smooth finish, reducing surface roughness and subsequently drag.
The turbine was tested in the Donald Campbell wind tunnel using a setup with a grease shaft, flexible couplings and a data recorder. The turbine properly self-started at a wind speed of 13.4 meters per second, and following that was able to run at 12, 10 and 8 meters per second. It also survived wind speeds over 80 meters per second, with RPM exceeding 5,000. Unfortunately, it was unable to run at the last test speed of 6, stalling at 6.1 meters per second, and the RPM dropped rapidly from the value of 1400. The CSR at maximum power achieved with a design speed of 10 meters per second is very close to the design CSR of 4.5 and stands at 4.61, which is a difference of just 2.4%. Interestingly, it also coincides with the mean value for the 3 tests, with equal separation of the peaks of the curves.
Overall, the turbine performed very well in testing. The fact that the turbine did not self-start was due more to the setup of the experiment than poor design. It has been shown in industry that drag reduction devices such as winglets can improve performance, and given more time, this would have been an avenue for further research and experimentation.